Thank you for coming. I'd like to thank the Geochemical Society, President Lee Sykes, and the members of the Patterson Award Committee. I also want to express my gratitude to Michael Cheller and Rod Ewing for the nomination. I'm pleased to accept this award on behalf of my research team, including the many dedicated students and collaborators who have worked tirelessly alongside me. I'm deeply honored to receive this prestigious award named after Professor Clair Patterson, who determined the Earth's age to be 4.55 billion years and fought valiantly against the hazards of lead contamination. So when I was a PhD student, I had two small portraits on my desk, one of Marie Curie and the other of Clair Patterson. His work profoundly influenced my journey as an environmental scientist. So this recognition stems from my research into the environmental chemistry of blood nuclei released during the Fukushima Daiichi nuclear power plant accident 13 years ago. Particularly the unique behavior of these radionuclides in particle form and their significant environmental impact. I'm gratified that this award brings renewed attention to the ongoing challenges of Fukushima, both in environmental and decommissioning efforts. It signifies that the geochemists still remain committed to contributing scientifically to the complex issues at Fukushima and other nuclear legacy sites. After I began writing this acceptance speech, I received the sad news that Professor Rod Ewing, who had just given the citation speech for this award, passed away on July 13th. The news shocked me deeply. Although it may be unusual, I decided to rewrite this speech to share some personal memories of Rod, which are relevant to this award. So Rod was a giant in our field and a mentor who cared deeply for his colleagues. I'm fortunate to be among those he supported. 9 years ago, when I was grieving deeply after my wife's passing, Rod encouraged me in his unique way. He secretly nominated me as a plenary lecturer at the Goldsmith Conference in Yokohama. It was a surprise, but I managed to give a talk about cesium-rich microparticles released from the Fukushima Daiichi, which attracted a wide attention. That opportunity propelled me to delve deeper into Fukushima research. During this work, I witnessed the physical and mental suffering of many residents, which led me to question how we, as geochemists and mineralogists, could contribute to addressing this tragedy of nuclear disaster. Although I never found a clear answer, I focused on the research and sharing our findings with the public. So when I started this Fukushima research, instead of forming a domestic network, often influenced by the perspectives of the Japanese authorities and TEPCO, I established a small independent and international collaborative network. This includes experts like Bernd Grambo of Nantes University, Gareth Lowe of University of Helsinki, and Rod Ewing of Stanford, who are all leading figures in nuclear material sciences and environmental radiochemistry. As Rod mentioned, I faced criticism and accusations in Japan when we published a series of articles. I didn't want to yield to any threats to science. Rod was even more steadfast. in this regard. He's helped me overcome obstacles and even assisted in securing our sample. During this challenging period, Rod was a beacon of light in the dark and a compass guiding us through the rough seas. Rod also has a knack of surprise. To be honest, I had no idea I was being nominated for this award. Rod had only mentioned that he had a nomination for geochemistry fellow. But knowing how much I respected Clair Patterson, he secretly put my name forward for the Patterson Award. When I received an email from Liz about this award, I was completely puzzled. It was not until later that I realized that this was the greatest surprise orchestrated by Rod and Mike. Looking at the past recipients of this award, including Mike, I see a list of superstars whom everyone admires. This recognition not only brings honor, but also a great sense of responsibility. I am resolute in my commitment to advancing our understanding of nuclear disasters, environmental challenges, and enduring complexities at Fukushima and other legacy sites. I feel that Clair Patterson is always watching, ensuring I'm staying on the right path. So there are too many colleagues to thank individually: Mike, Bernd, Gareth, and Arthur, to name a few. My apologies for not being able to mention all the names. I extend my deepest gratitude to my current and former students for their unwavering dedication to the Fukushima project, as well as to my Japanese colleagues Shinya Yamasaki, Kenji Horie, and Toshio Nuki, and my PhD supervisor Takashi Murakami. I cannot thank Rod enough. Beyond being a great scientist, he was a man of integrity, kindness, and fairness. I was very fortunate to work with him and to have published over 70 papers together. Rod, you promised you would attend the ceremony online. I believe you were watching from somewhere above. This medal is a gift from you. Thank you. Finally, I'd like to thank my family, my parents, and my precious daughters, Saiki and Yuna. I'm not sure I have been a good father, but I've always tried my best. To my dearest wife, Sachiyo, who passed away 9 years ago, you have always been in my heart and encouraged me to pursue this research. I wish you could be with me today to share in this honor. This medal is dedicated to you. Thank you all for giving me an opportunity to share my thoughts on this award. In the next 25 minutes, I will present some of the important research our team has published over the last decades. I hope you enjoy it. Thank you all. So as I said, I'm talking about cesium-rich microparticles released from Fukushima Daiichi. Some of you may have already have remembered there was a nuclear accident at Fukushima Daiichi in 2011, and about 520 petabecquerel of nuclear radionuclides were released, excluding the noble gases, and transported along the plumes to the distance and deposited, resulting in this contamination on the surface soil. So when you take radiographs of these surface soils, you take the image like this. Soluble cesium is tightly is diluted and tightly bound to the frayed edge side of the clay minerals, and then it shows up as a brighter contrast, like a green in this image. In addition to that, we found a number of very tiny hot spots, as you can see in this image in a red color. We didn't know what they were at first, but subsequently we and other scientists identify these hotspots as cesium-rich microparticles. So these particles are composed of silicon, iron, and zinc and cesium mainly, and the cesium activity ratio is about 1, and the cesium concentration is about 10 to the 11th becquerel per gram. And this activity ratio of around 1 indicates that these particles actually form inside of the reactor and release to the environment. So because of this high radioactivity, we wanted to know there was a demand to know the distribution of this kind of CSMPs in the environment. So we developed the new method to quantify the CSMPs and successfully apply to the indoor and outdoor samples. But I'm not going to talk about this aspect this time. But on the other hand, we actually we think these particles, as I said, these particles formed inside the reactor. So we thought that this is a good, the important media that retains the information on the reaction process during the meltdown event and the property of the debris. So I'm talking about these aspects in this talk. So first, I got interested in the internal structure of these particles. And of course, we use a transmission electron microscope to analyze these particles. So, but we need to make samples. We have to retrieve these particles first from the almost infinite numbers of the soil particles. It's quite difficult to isolate these particles. It took 4 months to find the first one. But eventually, we got several particles, and then we brought these particles to the focused ion beam, and then made a thin foil, and then analyzed cross-section of these particles, TM. So this is an example of the SEM pictures of CSMPs collected from Tokyo and Fukushima. As you can see, these SEM images shows some spherical shaped particles as small as less than 1 micrometers. And the cesium activity of these particles is around 1 becquerel or so. And sometimes we have 100 becquerels. So as I said, the cesium activity ratio is about 1 for these particles, and so these came from the Fukushima Daiichi. And when we look at the cross-section of these particles, we get this kind of images. This is a Halley stem image of and which the contrast of the Halley stem image is proportional to the G-square. So that means the heavier element shows a brighter contrast. And this is the elemental map of this cross-section. And you can see that the cesium is distributed heterogeneously, and the other elements actually are distributed homogeneously inside of the particles. And we also found some inclusions inside. And the nanoparticles. We also found the nanoparticles and of intrinsic cesium phase as inclusions. In this case, we found the cesium OH, and there's some silver telluride and selenide and cesium chloride. Based on these results, we actually propose the how these particles form. We actually propose this molten core concrete interactions for the formation process of CSMP. In MCCI actually, during the meltdown events, the melted core at the temperature higher than 2,000 degrees Celsius actually hits the bottom of the reactor pressure vessels and then melted through and then dropped immediately to the concrete pedestal of the bottom of the PCV, and then the concrete immediately volatilized and to form the CSMPs. So then we got interest in the isotopic ratio of these particles, and to understand the isotopic fractionation during the meltdown events. Here are some particles we found for the isotopic analysis, and we use the shrimp machine located in National Institute of Polar Research in Tokyo. So there was the isotopic interference between the cesium and barium. So it's quite problematic. So, but based on the evidence that this barium in CSMP is almost all of them are decay daughters of cesium. So we could actually solve this isotopic interference. As you can see, this is the results of the Simpson analysis, and this is the results of the gamma analysis. And the SIMS data appears to be plotted a little bit lower than the real isotopic ratio. This is because of the differences in the ionizing efficiency between the cesium and barium. So based on these differences, I actually put the ionization efficiency factors like this, and then we actually made this equation and solved this equation. We were able to determine this F as a 0.24 for CSMP metrics, and we are happy that this F value is very close to the F of the standard samples. We were able to distinguish these barium and cesium isotopes. So this is the result of the uranium isotopic ratios 235 to 238. It's very interesting because these the real data is plotted between the non-radiative fuel and calculated values. So this strongly indicates that there's a variation in the VANUPs in fuel assemblies. And also it also indicates the partial oxidation of uranium because it's quite difficult to volatilize the uranium in a tetravalent state. But we found the evidence of the volatilization of the uranium, so it means that the uranium actually presents as hexavalent. And we also did get some isotopic analysis for the potassium and calcium. Those are revealed natural origin, and rubidium isotopes so showed that this rubidium is radiophysiogenic. So this was the first isotopic analysis on individual CSMPs, and we were able to determine the origin and the isotopic fractionation of these isotopes. So it was the particular, very important insights to understand the behavior of radioisotopes during the meltdown events. So then we got interested in the uranium dioxide, because the uranium was used in nuclear fuel, and but during the meltdown events, it's actually melted, mixed with the structural material, and we didn't know that the property of this debris material. So there was a computational studies which reported this inconsistent results of the composition of the debris. This is because they did not know the composition of the real composition of the debris material. So the purpose of this topic was to elucidate the formation process of the debris fragments and to give some insights into the property of debris. But it was very difficult because the uranium content, the amount of uranium released to the environment is only 150 grams. So, but my students were very patient to find this uranium, and so we've actually found uranium nanoparticles associated with CSMPs, as you can see here indicated by red arrows. We found 13 nanoparticles of uranium in total. This is one of the examples. We found these uranium particles here outside of the CSMPs. But this was actually not the uranium. This was iron particles, but it contains uranium nanoparticles. As you can see here, under the TM half-stem image, the uraninite nanoparticles actually showed up brighter contrast. And you may say this is, maybe this is a natural origin and just attaching on the surface of the CSMPs, but this actually, we did the line scan analysis from traverse from A through B, and then we found that the molybdenum, technetium, this is evidence of these particles. These particles actually originated from the inside of the reactor, because there's no technetium in nature. So this is evidence of the debris fragments. So when we go further into the higher magnification, we start seeing some small dots, like here. And when we take the diffraction pattern, we were able to characterize this is uranium particles surrounded by the magnetite structure. And then if you go further, higher magnification, we start seeing the real atoms of the uranium and the iron. And actually, they're already epitaxially. So this is the evidence of the epitaxial growth. And also you see here that the 3D tomography of these nanoparticles, and it shows the euhedral shape. So this means that this is the evidence of the slow and epitaxial crystallization of magnetite. And we found 11 particles in this CSMPs, and with the composition of uranium zirconium eutectics. And this is one of the examples of the high resolution, and we identified the uraninite structure when we have a higher uranium concentration, and if you have a low uranium concentration, these particles have a cubic zirconia structure. This is indicative of the very rapid cooling, because the cubic structure is a high temperature phase. So based on this, these data, we could extract some part of the melting phenomena that occurred inside the reactor. For example, the uraninite slowly cools down, surrounded by the iron oxide, and then also found the zirconium uranium cladding, eutectic. So this is this is the evidence of the rapid cooling, and we also found this association of these uranium nitrogen particles with CSMPs, and this is an important medium transporting debris fragments into the environment. So we were able to characterize uraninite. So what comes next is the plutonium, because plutonium is very radiotoxic, and in case of Fukushima, they were using the 540 irradiated fuels, and which contains less than 1% of plutonium. And they also used, they were using the 32 MOX fuels, metal oxide, mixed oxide fuel, which contains 4 to 9% of the plutonium isotopes. So that was a big concern. So we wanted to know the plutonium distribution in the environment. But fortunately, the concentration was very, very low, as you can see here. And some previous study suggested that the low concentration of plutonium is due to the volatility of the plutonium. So they considered that plutonium was volatilized similarly to the cesium and then transported to the environment. But there was a question that in terms of the plutonium occurrence in the debris and this kind of release mechanism. And the most importantly, it was very difficult because the concentration is much lower than the uranium. It's only 580 milligrams of plutonium was released to the environment. But it's very, very difficult to find. But fortunately, we detected under the Simpson analysis. And this is one example, the 240 to 239 isotopic ratios of the individual particles. And these particles, these data is actually consistent with the bulk analysis and the calculation value. So 242 to 239 isotopic analysis showed almost a similar tendency. So in addition to that, we actually brought the same sample, same particles to the synchrotron facility in Diamond in the UK, and also the Swiss light source. And we did the XRF analysis, and we found the uranium distribution like this. But actually, this uranium distribution consists of several nanoparticles of uraninite, because we took this image from the same particles as well. And then we tried to find the plutonium, and that's the spots with uranium, high uranium concentration. But unfortunately, we didn't get plutonium from this white color arrows, but only one spot indicated by red. We actually got the absorption edge of the plutonium L3. So it reveals the white line that corresponds to the plutonium oxide. It's quite difficult to distinguish the plutonium oxidation state of a plutonium, but in this case, I can just say like plutonium oxide. So this kind of distribution is quite reasonable because when you have irradiated fuels like Fukushima, we got this kind of micro concentration of plutonium only at the edge of the rim part of the fuel pellets, which is very close to the zirconium claddings, because we found the plutonium very close to zirconium. So this is the evidence that these particles still remain the texture, original texture of the irradiated fuel. So the summary of this topic is that we found the first particulate form of particulate plutonium from the Fukushima Daiichi, and the isotopic ratios are consistent with the ones calculated with origin calculation. And importantly, debris fragments with plutonium was really associated with some CSMPs and dispersed in a particulate form, particle form. So, okay, so we got interested in the boron, but I do not have time today. But so I am going to give a talk on Wednesday this session. So briefly, we've actually found the direct evidence of boron, the volatilization of the boron carbide control rod. So I'm going to talk in this topic on Wednesday. Sorry. So the last topic is the direct observation of the radioactive cesium atoms. The motivation of this topic is very simple. I want to be the first person to detect, to look at radioactive cesium atoms. But it was very difficult because it had CSMP has the high concentration of cesium, although some CSMP contains polysite, and the polysite is very sensitive to electron beams, so it's susceptible to radiation damage. But the susceptibility depends on the composition. So we try to find the composition very resistant to the electron beam, and then we found one particles, and then we got this kind of image showing the bright spots, or array of the bright spots. As I said, the Halley stem image contrast is proportional to the Z-square. So the heavier elements show the brighter. In this case, cesium atoms show the brighter contrast. But unfortunately, 011 direction, we found overlap of the other cations, so we couldn't actually distinguish this cesium from the other cations. But when we look at this structure from the 111 zone axis, we realized that the cesium actually sits on a specific sites. Only cesium atoms appear at these specific sites. So we immediately went back to the TM lab and then took some TM image. And then this is what we got. You can see here that there's some white spots that correspond to the cesium atoms, and only cesium atoms. And actually arrayed in 6-fold symmetries. This is a good evidence that we actually were able to image the cesium atoms. Well, we cannot say this is all radioactive cesium because it has some stable isotopes, but half of these spots represent the radioactive cesium atoms. So this was the first image of radioactive cesium atoms. But and also this actually suggests some important insights, like a local high concentration of cesium in MCCI reaction during meltdown events. So to conclude, so the nuclear disaster at Fukushima Daiichi left many unsolved problems. It released a huge amount of radionuclides, including tiny CSMPs. So our work is one of the good examples of geochemist contributions, showing that state-of-the-art analytical techniques can retrieve various insights into the phenomenology of the accident. I think this is very important. This type of work is very important, sorry. Especially, we are facing nuclear crisis in Ukraine right now. Thank you for your attention, and I'm happy to take any questions.
Well, thank you very much for the talk. It was very interesting. Unfortunately, because we messed up with the video, we've run out of time for questions, but I'm sure that people can approach you at some other point and ask you questions. Wow. So I would like to call our next speaker. That's all staying in cesium studies. Let me